Hello, welcome to this video on the dot product. It's actually a series of videos. There most likely will be 4 of them. This is the first one, just an introductory video. We've seen in the past that we could take 2 vectors and we could add them. We could also take one vector and scale it. And so the question becomes, what happens when it comes to multiplying 2 vectors? Is that a thing? And if not, why? Or what can you do with it? And so adding 2 vectors yields another vector where you take component-wise, you add them together. So one would think, okay, well, why can't I do the same thing with multiplication? Multiply component-wise and make a vector out of that. The answer is no. The product of 2 vectors yielding another vector where the corresponding components are multiplied, never in the history of anything has that been a useful object or meaningful object or anything like that. Okay, but when it does come to product of 2 vectors, we'll find that there is a vector that you can get by taking the cross product of 2 vectors. And what we're going to find out in this lesson is that there is a number that you can get by taking the dot product between 2 vectors. So when it comes to products, there's 2 of them. The dot product gives a number and the cross product gives a vector. So the next series of videos will be on the cross product, but this series here, about 4 videos, will be on the dot product. Simple calculation. Component wise, we're going to multiply and we're going to add them up and get a number out of that. Okay, so 2 vectors come in, 1 number comes out. It's called the dot product. All right. Sounds good. Simple calculation. Let's see it. 2, -3, 4, 0, 6, 5. Multiply component wise, add them up. So we get a 0, a -18, and a +20. The dot product between those 2 vectors is 2. Just like that. Easy calculation. It's going to be one of your favorite calculations to make. It's amazing how useful it is and the properties that are possible, behind it. This is directly related to the angle between the 2 vectors. It's crazy, but true. All right, let's take a look at some of those properties. So you have 3 vectors, u, v, and w, and we have a scalar c. Now think of the calculation that we're doing, multiplying component wise and adding them together. So the first property hopefully makes sense, that the order in which you do your dot product shouldn't matter. U dot v should be the same as v dot u. Because component-wise, you're going to multiply, and those real numbers are commutative, so the dot product is commutative. All right, great. What about associative? Say you want to add 2 vectors first, and then dot it with the 3rd vector. Well, I'm sorry, not associative. What did I say? I'm sorry, distributive. We're going to distribute. You can dot that vector with each of the other 2, and then add afterwards. So on the left-hand side is add first, then dot. And on the right-hand side is dot first, then add. Distributive. Dot product is distributive over a vector addition. Okay, now this next object seems kind of strange. It's a dot product who is then multiplied by a constant. So you get a number out of the dot product, and then when you see 2 numbers written next to each other, that's just multiplication. But what you can't do, though, is distribute that scalar across to both vectors. Okay, that doesn't work out. And so you could scale one vector and then dot with the other. You could reverse that and scale the other vector and dot with the other. But when it comes time to scaling both, you don't do that. Okay. All right, great. There's a vector out there called the 0 vector. It's a vector that's full of zeros as its components. Dotting anything with that, of course, is going to be the number 0. So if you ever see a bold 0, I'm discussing the vector 0. If you ever see a regular looking 0, that's the number 0. Okay. This next one might be the most useful of all. When you dot a vector with itself, you get the magnitude of the vector squared. Because think about what you're doing. You're squaring each component. You're doing v1 or v1 times v1 and v2 times v2 and v3 times v3, and then you're adding them all up. So yeah, you're getting the what's underneath the square root in the magnitude. Okay, and so the magnitude of the vector squared is equal to the dot product of the vector with itself. So keep that in mind. Put a star by that one. That's the most useful. And number 1 as well, the fact that it's commutative. Okay. All right. So then we have a series of questions here, just trying to see if what comes out of this is a result that's useful, a meaningful result, okay, or even possible at all. All right. In the first one, we have, now if you ever see a dot now, you got to worry about like what is going on with this dot. So dot is going to mean dot product for us. 2 vectors with a dot in between means that you are going to have a number that comes out, this dot product that we're calculating. So on the left here for letter A, we have a number. It's from the dot product of u and v. But then that number is dotted with the vector. That's not something you can do. So the dot is not going to indicate scaling the vector. When we want to indicate scaling the vector, we write the constant next to the vector. And so left hand is a number, right hand is a vector. You can't dot a vector and a number. You can dot a vector and a vector, but you can't dot a vector and a number. So this is not possible. It's not meaningful at all. It's useless. Notice the contrast between A and B. In B, there is no dot before the W. So you'll still get the dot product from U dot V. And when it's written next to W like this, that doesn't mean dotted with W, that means scaled W. So W is being scaled by the dot product between U and V. So yeah, that's a very possible thing. Okay. Basically, the difference between B and C is that the order is reversed. I don't know why that's, except for we have a scalar and a scalar written next to each other. See, that's the magnitude of U, and then we have our dot product between B and W. So that's a number for the magnitude, that's a number for the dot product. Those 2 numbers written next to each other means to multiply those 2 numbers together. So yeah, that's meaningful. Okay. Letter D is from the previous slide, adding 2 vectors and then dotting with a third. Yeah, that's definitely meaningful. Letter E, you're going to dot U and V. I guess you're going to go left or right. You're going to dot U and V. See, without any indication of the parentheses, the difference between D and E is that there's no parentheses. And without those parentheses, you just go from left to right, and dotting gives you a scalar. You can't take a scalar and add it to a vector. Okay. And then lastly, we have a scalar from the magnitude of U, a scalar from the dot product, but then there's a dot in between. Contrast that with letter C, basically. In letter C, there's no dot in between. Those 2 scalars get multiplied. But in letter F, there's a dot in between. You can't take a scalar dot with a scalar. That dot means dot product between 2 vectors. Okay, great. Well, this ends the video on just an introduction to what the dot product is and what are its properties. And so we'll get into why we care about it in the next video, because we'll tie it to the angle between the vectors. All right, my name is Nakia Rimmer. Thank you for watching. I'm here to help you through this Calc 3 journey, multivariable calculus, trying to get a good grasp on vectors before we bring in vector functions and then multivariable calculus. And so please comment down below, like and subscribe. If you have any questions, please seek out my help, and I'll see you in the next video. Take care.